Okay, so I'm going to teach you about a kind of diagram that's called an LOL chart. We're going to use it to model interactions or energy transfers. And so we're going to start with a simple one, where just a ball is falling. Okay, so it's going to start with position A where it's up in the air, and it's going to end in position B as it hits the ground. Okay, so when it's up here in the air, it's got height, and as it falls, it loses height and gains velocity. Well, if we want to look at it from an energy perspective, what's happening is it has potential energy because it's in Earth's gravitational field, so it has gravitational potential energy. So we're going to create a bar here with, I'm going to put 4 boxes of energy. Just whatever you put here, however many boxes you put, is just kind of an arbitrary way of showing energy transfer. So the number of boxes that you put at the beginning doesn't really matter. It's kind of up to you. And what's going to happen to this ball is that as it falls, that gravitational potential energy is going to decrease, which is going to cause the kinetic energy to increase. So there's a transformation of energy. Okay? And that energy is being transformed from gravitational potential energy to kinetic energy. And so as it approaches the ground, all of that gravitational potential energy has been transformed into kinetic energy because of velocity. So it's going from height to velocity. Now some important things here. First of all, the total energy here I started with and the total energy here that I'm ending with are the same. Okay, that means that the total energy in my system is conserved, and that's a good thing. That's what we're hoping for. Okay, a piece that I forgot here was to define the system. So this system would be the ball that's falling, and we're actually going to include in our system the Earth as well. The reason we're including the Earth is because it has gravitational potential energy due to its position relative to the Earth. We're going to say it's a closed system because the total energy of the system will be conserved. And now using this, I can actually write an equation. I can say that mgh, okay, my gravitational potential energy, is equal to my kinetic energy, 1/2 mv squared. And then I can use this to solve for, if I knew how fast it was going to hit the ground, I could use it to solve for how high it was falling from. Or if I know how high it fell from, I can use it to solve for velocity. The last piece that we need is to just give a statement of the energy transfer. So you'll write out in complete sentences what happened. In this case, gravitational potential energy was transformed into kinetic energy. Okay, and so this is our transformation. It's a statement of our transformation. Or we could be more specific, the gravitational potential energy of the ball into kinetic energy as it fell. Okay, so let's give maybe one more example here. How to use these charts. All right, let's do a similar example. This time we have a ball that is falling. Okay, let's say it's falling from a height of 4 meters, and that when it hits the ground, so this ball is falling. Okay, let's say it has a mass of 0.5 kilograms. Okay, and that when it right before it hits the ground and gets to this point, it's going has a velocity of 5 meters per second. So here it's at rest. As it's approaching the ground, it's at a velocity of 5 meters per second. Okay, so for this one, we're going to model the energy transfer. Okay, and it's going to turn out that for this one, some of the energy is actually lost because it should be going faster here. And so we have to account for the fact that it's actually not going as fast. So just like the last time, we're going to start with gravitational potential energy, and that gravitational potential energy is going to decrease and be transformed into kinetic energy. Okay? But there's something else going on here too. The last time it was a closed system, the same system the ball on the Earth, but this time it's an open system, meaning that energy can be lost. Okay, which means that energy is leaving the system in the form of thermal energy. Okay, so if we started with 4 boxes of gravitational potential energy, maybe we only ended up with 2 boxes of kinetic energy. Okay, and the rest of it was lost forever in the form of thermal energy. And I'm going to shade this in to show that's energy that can't be gotten back. Okay, so this is energy that's been now lost to thermal energy. Okay, causing the environment to warm up, okay, the area around the ball. And so anytime when we expect something to have a certain speed or go to a certain height, but it doesn't, that's because energy was lost. In this case, it was lost through the thermal energy. Well, now we can write our equation. Okay, so now we can write our equation. mgh for gravitational potential energy. We put an equal sign under our transformation here. And then we end up with kinetic energy, 1/2 mv squared plus our thermal energy. Okay? And so now we can do a couple of things. We can find each of these energies. We can find out how much thermal energy was created. And we can even find how efficient the ball drop was. Okay, so to do our calculation, actually you can go ahead and do the calculations. Find the potential energy and the kinetic energy and solve for the amount of thermal energy created. Okay, so potential energy, 0.5 kilograms, 9.8 meters per second squared, times a height of 4 meters. For kinetic energy, 1/2 times 0.5 kilograms, times a velocity of 5 meters per second, and that's squared. Okay? So 19.6 joules of potential energy, 6.25 joules of kinetic energy, and then E thermal is going to be, you can solve for that just by subtracting those over. And get 13.35 joules of thermal energy created. Okay, the last thing we can do is we find the efficiency. That would be energy out divided by energy in, and multiply by 100 to make it a percent. So the efficiency here would be equal to about 32%.